Um, so good afternoon. Talaat Khalil from data scientist from Booking.com, and we want to present our use case of OpenNMT and how we handle the issues that we have, and some recommendations and feature requests. So basically, this is how the presentation will go. We'll start with the use case in Booking.com and why do we need machine translation, and then some information about pipeline, like and the standard architecture. Then we'll go to our evaluation pipeline, some of our trials for domain adaptation for user-generated content. And yep, it's good enough. Yeah, thank you. Some of the challenges that we have in translation, our approaches, some of them are resolved or handled in some way or another. Some other challenges are not, and some information about our production pipeline, some recommendations for the community, and feature requests, and finally some references. Basically, maybe some of the of my slides will be a little bit outdated because since the morning we had like new information about OpenNMT and like new implementations and like future plans. So you'll find some outdated things, but should be okay. Why do we need like machine translation in Booking.com? Because basically we have like 2 out of 3 of the bookings that we have are made in language which is not English, and basically we need to like give locally relevant content to those users, and and for hotel descriptions, for example, like in our use cases, we have like hotel descriptions, room descriptions, and the user generated content, which in terms of reviews or emails or whatever. So our main use cases are basically from hotel and room descriptions. So when you open like the hotel page, you'll find like brief descriptions about the hotel, and some descriptions of the rooms also. And those are like, we have like more than 1 million properties, and those translations, it's not only about translating untranslated properties like from English to other languages, but also updating the descriptions, because every day new descriptions are updated. And for big languages, like high demand languages, we have only like 50% coverage by human translations. And human translations, it's basically translated by our freelancers network. And this covers like 90% of the demand for the high demand languages. And our translation memory for those languages, translation memory is basically or mostly dominated by hotels and room descriptions. For like high demand languages, we have on average like 10 million parallel in domain sentences. And another use case, which is user reviews, where we don't have any translated content at all. No translations are available, no human translations at all. So basically no in-domain data, and we needed to tackle this in different ways. So this is like our basic pipeline, more or less. So basically, like we start with pre-processing and like data cleaning, and for some use cases and languages, we handle numbers and named entities. We'll discuss this later, and then OpenNMT pre-processing, we add some domain-specific features also. And then we train like sequence architecture, and this is described in the next slide. Sometimes we do domain fine-tuning, either for a specific domain like hotel descriptions or room descriptions, or it's necessary in other cases like user-generated content. We do translation like normal translation, but before like translating, we try to select like the best input for the translation system. So we can like input one sentence to the translation system, or like a couple of sentences, or like different combinations, and we have like ranking system, like to rank like whether to input like only one sentence or two sentences concatenated together to the system, like depending on whether like one system will be most similar to the training set, or two sentences or so. So we try to make the input for the translation system as similar as possible to the similar sentences in the training data in terms of the structure. And this helps like to boost the performance. And finally, for pre-processing, we like handle numbers and named entities again, and try to predict like mistakes in the translations so that we can handle it. And finally, evaluation, like automatic and human evaluation. This like briefly like the architecture. If you're familiar with OpenNMT, you'll be familiar with these options. So we use like byte pair encoding, and we use like input dimensions and hidden dimensions of like 1,000 encoder and decoder layers, like 4 hidden layers. We use bidirectional encoder, and we use residual connections mostly. And when we started like development with OpenNMT, we started with SGD optimizer. Basically, we started development with OpenNMT 8, and our main production version was OpenNMT 8, and the stable implementation was stochastic gradient descent. Later, we experimented with Adam also. Like our stopping criteria is based basically on the perplexity, the validation set perplexity. So we don't stop after X epochs, for example, but we stop when we see no decrease at all in the validation perplexity for like many epochs. Like if we have like 5 or 6 epochs without any change in or any decrease in validation perplexity, then we stop the training, just to make sure that the model converged. And yeah, for training some other information, like we use like NVIDIA P100 GPUs to train our systems. For the evaluation, we use BlueScore for model development. So to compare different models during development, and in our validation experiment, we depend on BlueScores to choose which model or which models to test. And then we do human evaluation, adequacy and fluency check. So we take samples from our translations and send it to our language specialists, and then they give scores. And based on these scores, we decide if it's good enough to go for an A/B test or not. And we have biased sample evaluation, where we try to detect the sentences with like a high probability of like being of having like errors in the translations, and we try to evaluate this by humans also to see what kind of mistakes are like produced, and like how to tackle these issues. So I'll go through like so for hotel descriptions and room descriptions, basically. We just use the architecture with the in-domain data. We have lots of in-domain data, like 10 million sentences per language or so. So it's not a big issue. And we use the standard architecture that I described earlier. But for user-generated content and mainly reviews, we have like a problem is that like we don't have in-domain data at all. And we try to translate some in-domain data, but like we can hardly have like 30,000 to maximum of like 70, 80,000 like for some top languages. So it's not an we don't have like plenty of data for user-generated content, and so we had to depend on publicly available data. to train model with publicly available data, or to use the publicly available data in one way or another. So we got data like from movie subtitles, from Wikipedia, TED Talks, news commentary, and Europarl. Also, we created the synthetic data with back translation, as discussed in the previous presentations. But in our case, we just used one back translation model, not like 4 back translation models or so. And that was like the first thing, synthetic data as described by Rico Sinrich. And the other, and then after creating the synthetic data, we then use one of 2 approaches. Like either we use an approach which is called like gradual downsampling. It's described in paper by Wees et al. In University of Amsterdam. Or we do like normal fine-tuning, where we train using the general domain data and then fine-tune only if we have like in-domain data. I'll go like quickly through the approaches. So for gradual downsampling, we have like the out-of-domain data, and we have like the synthetic data, which is in-domain data, like with mistakes, of course, because it's like it's generated by back translation. And if sometimes we have in-domain data in some languages, in other languages we don't have in-domain data at all. And basically, the idea for this gradual downsampling thing is to get from the out-of-domain, rank the out-of-domain data sentences based on their relevancy to the in-domain data. So we have a lot of reviews, monolingual reviews, but not parallel data. And we want like to find like the sentences, to rank the sentences which are very similar to the in-domain data higher, and which is also like not that similar to the general data. So the sentences which are very similar to the in-domain data but not that similar to the general data are ranked higher in our in this like out-of-domain data. And then we train gradually like this. So at first we train with the whole data, for example, and then we keep the in-domain data in all the epochs. But after X epochs, like these numbers are very like it depends on your data, and it depends on the experiments. Like we ended up with like reducing, for example, here like we start with the whole data, then we take the whole in-domain data, but we reduce the out-of-domain data with like the most 80% relevant data, and we like sample the synthetic data randomly by 80%, and then after 2 epochs we downsample again by 80% for the out-of-domain data to the most relevant examples, and keep the in-domain data, and so on until the model converges. And like if we have in-domain data, that's the good case. But at least if you don't have in-domain data, it's preferable like to have some in-domain data just for validation, to use it as validation set, to know like when to stop if you want to like do early stopping for your basically those numbers are like kind of hyperparameters, like the 80% thing, or like to wait 2 epochs and then reduce. We ended up using like reducing the data by 50% for every 4 epochs, like one of the good configurations that worked for us. But I think it depends. And fine tuning, it's the most popular approach. It's just like to train with the whole open data, like the publicly available data plus our in-domain translation memories, and then wait until the model converges, and then fine tune with the in-domain data. But yeah, this kind of comparison, like for gradual downsampling, it's quick, like because we reduced the data like by, for example, 50% after every 4 epochs or so. So you can train the system quickly. So if you want to put things into production quickly, or you have like, I don't know, business goals at the end of the quarter, so it might be good thing to do. on the other hand, like fine tuning, if we have like 50 million sentences or more, and then you need to train the model until convergence, that this takes a lot of time, especially if you train like with single GPU or so, or you have to, even if you have more resources, I think it's still tricky. For the gradual downsampling, it's like you adapt to a specific use case from the beginning, but for fine tuning, you can adapt to, you can train the model once, but then the process will be much quicker because you can adapt with any in-domain data. For gradual downsampling, you don't really need in-domain parallel in-domain data, but you need like just like monolingual in-domain data to rank the out-of-domain data based on this. But for fine-tuning, you really need in-domain data. And according to our experiments, like if you do fine-tuning, you'll have more accurate results than even gradual fine-tuning, but it's just a trade-off. One unanswered question, like we didn't experiment. So if we have like general model without like gradual fine-tuning and without domain adaptation, will it perform like better than gradual downsampling or not? This is like not answered yet. So I'll discuss briefly some of our challenges, like in translation in general, and like some of like our approaches to fix this, like numbers translations. It happens a lot that we have numbers translated incorrectly, even if you have a lot of in-domain data. And like we handled this by introducing placeholders for distance, time, currencies, dates, and so on. Named entities translation, we followed the same approach, but named entities is still tricky because named entities can be mentioned in different ways, even like for hotel names or landmarks. It can be mentioned in different ways. Maybe you just mention the hotel by the first two tokens of the hotel name, and sometimes you mention the whole hotel name. And in production databases, there should be another, there could be another standard, and sometimes it's super tricky. Sometimes named entities are just like normal names and can be confused if you just try matching. So we tried to like train named entity taggers for some languages using OpenNMT also, and it's working. Like it's better than like rule-based systems, but it's still tricky to like tag the named entities, especially in our context, because like we have a lot of named entities. Like in our description, you can find like a lot of hotel names, a lot of landmarks, cities, countries, and so on. And for rare words translation, so at first we thought like, okay, we have like in-domain like 10 or 15 million in-domain sentences, so translations should be okay. We don't need any general general domain data for translations. But basically, on average, like if we can compare our system to like best general NMT general purpose models, in our in-domain data, like generally speaking, our model performs better and significantly better. But when it comes to rare words, rare words, then those general domain systems perform better than our system. And then we realized that we need, maybe even if we have like millions of in-domain data, maybe we need to like train on general data, all the available data first, and maybe fine tune with our in-domain data. Because sometimes also the data in the past like doesn't generalize well. Maybe some hotel descriptions in the future like can be written in different ways, and then you get like little bit different language, and you can't generalize even if you have like millions of data samples. Repetitions and omissions, it happens, and I think it's related to rare words also, or like strange language compared to the training set. Something like peace and tranquility, for example, is translated as like peace and peace. Some translations are like this, and things sometimes are related. There is an interesting paper from Ramachandran et al. And they incorporated language models, trained on general data in the encoder and the decoder. So they trained those language models independently at first on general data, and then they initialized the neural network for the encoder and decoder, the embeddings and the initial layers with those language models, and later they continued the training for two objectives, the translation objective, and also continued training the language model to avoid catastrophic forgetting. I think if we have something like this in OpenNMT, that could help a lot in such cases like real world translations and maybe also in domain adaptation, if we can have those language models for domain adaptation. In accurate source language, it's something like you can clean your data, but in the end of the day, even the input data for your system can be inaccurate from grammar and punctuation point of view. It's still tricky. We haven't tackled this yet, but it results in inaccurate translations also sometimes. Context handling, especially in morphologically rich languages like Russian and Arabic. We have over 10 million data sets for Russian and Arabic, so it's not low resource languages in our case, but still we have problems with the context because in these languages, like in English, you can have the hotel is located in Paris, and then a new sentence like it features free Wi-Fi, for example. But then it features free Wi-Fi in Russian or Arabic. If you have it and you don't know the gender of it, then it might be translated incorrectly. So hotel can be have male gender, and chalet could be different. So depending on the property type, you have different genders. So you need the context from the previous system, and NMT systems mostly are trained on sentence space, and then you get these things incorrectly. For some languages, we introduced features for properties. So in the sentence, we introduced feature about the property type, whether it's hotel or hostel or chalet or whatever. So this helps in the translation when you include some context. But also there are some new interesting papers to handle this context issue. One of them is Bodin et al. And it's mentioned also in my references, where they tried to incorporate the context from previous sentences and use multi-encoders. Yeah, hopefully we will have some support from OpenNMT. For production pipeline, the ZeroMQ server provides good flexibility, but it's not that compatible with our HTTP based infrastructure. So we use a kind of batched version of the REST server. So we do all the pre-processing functionalities, we implement them separately, and then we use the OpenNMT REST server for translation. Not sure if it's maybe some things were updated regarding this, but yeah. Yeah, some more features. Instance waiting would be helpful, for domain adaptation or in many other cases, if we can wait the instances. And the way it's implemented in OpenNMT right now, we can oversample some examples, but this has a cost also, because when you oversample, you increase the training time. And but if you have instance waiting incorporated in your loss function, where you can wait the instances, wait in domain data, out of domain data, or explicitly in your loss function, then this we think that this could help. And like if we can have this ability of resampling the data across different epochs and adapt those weights, I think some of the interesting ideas were like discussed in Wang et al. Paper regarding like instance weighting and adaptive and adapting these weights across epochs or many batches. So this could be of an inspiration for us to include this in OpenNMT. Yeah, maybe like general recommendation, like we've been working with this like from a while, and like the general recommendation, maybe we need to start with like like data models trained on all the available data at first. It takes time, but maybe if we have like if we can like run this on enough resources, it would be okay. But in the end of the day, like having model like trained on the general data and then fine-tuned with whatever you want, like gives the best performance. And maybe it's a bit repetitive, but all of our recent we did experiment with tensor to tensor recently, and all of our recent experiments, like it's like consistently with the big transformer model, it's always consistently better than our best configuration using like sequence the sequence models for OpenNMT. And yeah, it's even like for German, for Dutch, for Korean, for Chinese, Japanese. We experiment Swedish and Norwegian, all of these languages. Like the transformer model was like significantly better in terms of blue scores and in terms of samples sent to human evaluation on sentence and paragraph level. Maybe a lower version is not needed, as I heard before in the previous presentations, because it will be obsolete more or less. But yeah, our production pipelines now are based on the lower torch implementation. So yeah, hopefully we'll have this implementation more mature in the other frameworks. Yeah. So some of my colleagues also asked for like multi-encoder support. We have other use cases if we can include like to the to have like multiple encoders, like images, and to include like input data from images and text and other contexts for translation. And finally, it seems like we might be moving to like TensorFlow based frameworks more or less, because like for us, like TensorFlow has more like proper versioning or stable versions than lower torch. It's more about research. Also like easier to install in production. I heard like maybe it's the installation part could be fixed by the wizards that were introduced earlier, but like deploying and the deployment and productionizing process for TensorFlow is like much easier and supported, at least in our case. And finally, thank you. And yeah, our team needs some more data scientists, so please feel free to contact me if you wanna have more challenges. And yeah, sorry not for including numbers, but I did this presentation in rush. But I'm open for any questions from you. Thank you.
Thank you very much. It's very interesting to see how far you have been using OpenMT and the needs to. Is there any question? One question quickly.
When you have user-generated content on a page, is it helpful to know what say the vocabulary of the hotel it's posted on, or like other aspects about the page generally, for kind of knowing the extra vocabulary that you might use or getting named entities right?
For like using vocabulary from the hotel page as features.
Yeah, if it's like a comment on a hotel page, would knowing the context of the whole page help out? And
yeah, I think it could be useful. Yeah. Yeah, thank you. There's a question there, I think.
Do you have any information about the kind of hardware that you are using in terms of scale? You mentioned 10 million sentences in parallel.
Yeah, for training, like we use NVIDIA P100 GPUs for training, and like even we use either like one GPU or a cluster of 4 GPUs that were like our recent experiments. But even with using like one NVIDIA P100 GPU, using 10 million sentences, you can using our architecture, you can the system like might converge within 2 weeks or something like this. Yeah. or a bit less, yeah, could be. If you use more GPUs,